Alright, welcome to MathLux. This is a video on the horizontal and vertical asymptotes of irrational functions, the types of asymptotes you will see when dealing with a rational function. So to start, a rational function is f at x over equals g at x over h at x. So it's a function where your polynomial is being divided by another polynomial where h at x is not 0. The denominator of this rational function cannot be 0. So some examples of this would be x squared plus 3x plus 2 over x to the power of 100 plus 37. Or you have this funny one with the vertical y equals mx plus b line dividing the rational function. That's how it would look if you graphed a function that the top is 1 degree higher than the bottom. That isn't something we'll be covering in this video, but just to let you know, that is a oblique asymptote, something we'll be talking about in the future. You have this f at x is x minus 1, x minus 3 over x plus 3 to the all that to the power of 3. And this would be another case of, well, actually I can't spoil it yet, but we'll be able to, by the end of this lesson, find the vertical and horizontal asymptotes of this function. You have y equals x over x plus 1, and then of course you have your v at x equals negative 1 over x. So I guess to start, after you see all this, you could probably take a guess and see that the base function for a rational function would be 1 over x, right? Where 1 is a x to the degree 0 polynomial, and the denominator is an x to the 1 polynomial. That's just the base one. Obviously, you can have different polynomials in that. And so I guess now getting into what an asymptote is. So an asymptote is a line that the function approaches but never crosses, okay? So take these vertical asymptotes, for example. These can be found by observing the roots or the h at x function or denominator of the function. Right, so in this first example here, we have 1 over x plus 1, right? So we take the denominator, we find the roots of the denominator. X plus 1 equals 0. We want to find where this term of x plus 1 equals 0. And that is true when x is negative 1. So we have a vertical asymptote right here at negative 1, right? Because you can't divide a number by 0, okay? So, right, if we do 1 over minus 1 plus 1, you have a number that is not possible. You can't divide a number by 0, hence why the function never crosses that. Now this one here, you have vertical asymptotes at 3 and negative 2. But in this case, there's something called a hole or a asymptote. Not a vertical asymptote, but just an asymptote. So since something on the top and bottom cancel out, you have this here, which is minus 2, and it actually doesn't interfere with the function because these terms cancel out. So basically it's saying, like a vertical asymptote, something cannot cross this line, but the function actually goes through that point, just never touches that point. So in a way, it's not a vertical asymptote. Something we'll be discussing in more future in the next lessons. But for the purposes of this, just treat it like a vertical asymptote. And then our other one will be at 3. So this would be 3, and this would be negative 2. The graph touches every number except those points, right? So x is an element of all real numbers such that x is not equal negative 2 and 3. And the range would be y is an element of all real numbers, except for the y value at that asymptote. So then lastly, you have this rational function here, and it's negative, so it's been flipped over the a value is negative, so it has been flipped over the I guess it would be y-axis. But anyways, the vertical asymptote for this one is just, when can this not equal 0? Well, when x is equal to 0, this function doesn't exist. So the vertical asymptote is 0. And now horizontal asymptotes, they're a bit more complicated. They can be found by observing the coefficient and degree of the leading term in the polynomial function in the rational function. So here you have f at x equals ax to the power of n plus a polynomial, and b to the x to the m plus the polynomial continues, right? So basically, how do we find an asymptote? Well, we examine the leading coefficient and the powers. So by looking at a, b, n, and m, we can find the asymptote, right? So we have, if the degree of the top of the function, the leading coefficient at the top of the function, is less than m, then the asymptote would be 0. So examples with this would be x over x squared. This would have in asymptote, y is not equal to, or y equals 0 would be its asymptote. So y will never touch 0. The function will never touch y equals 0. Because you see the degree of the polynomial was x to the 1 over x to the 2. And now if the degree of n is equal to m, then the asymptote's y value is a over b, these leading coefficients. So you have f at x equals 2x over 7x. So since these are both x to the 1, we ignore them. Well, we don't cancel them, but we ignore them and we look at, oh, it's 2 over 7. So that would be our horizontal asymptote, right? So yeah, because they're the same degree, we ignore them. So if it was a quadratic over a quadratic, a cubic over a cubic, and so on, it would have that pattern. And lastly is if the numerator is greater than the denominator, the degree of the denominator, then there is no horizontal asymptote. So this would be x to the 3 over x1. Now, in one situation, though, where the top is 1 degree higher than the bottom, then you would have something called an oblique asymptote, but that is something that we will not be discussing today. So there are 2 other types of asymptotes when talking rational functions that we haven't discussed yet. So one of them will be the whole, and this would be when you have like f at x over g at x, but both of them share a factor, so you can cancel that factor out, and it makes a hole in the graph. So there's no y or x value at that hole. It's a hole. It's the function stops for one point in time, and then it continues again. And then the oblique asymptote is like previously discussed, when the numerator is 1 degree higher than the denominator. Instead of getting a horizontal asymptote, you then get a y equals mx plus b asymptote. So your asymptote is actually a vertical line. But just to be clear, you don't need to understand this now. This is something that will be discussed in more depth in future rational function videos. And we will go into more depth about how to graph them, in addition to how to identify the oblique and whole asymptotes better, and I guess create your own functions and be able to manipulate them with k values, a values, negative a values, d values, and of course c values. So that was the MathLux video covering the basics of the common asymptotes you see in rational functions. New video next Saturday. Like and subscribe.